All right, folks. Hey, listen, I understand the 7:30 class is not fun for y'all, but you know, think about it as like practice for, I don't know, a job or something. Where you usually have to be there at 7:30, right? We good on that? And you get good parking. You get to see me at 7:30. Study physics at 7:30. It's a good thing, right? I'm sorry, what? Right. Yeah, I appreciate that. Grace, is that right? No. What's her name? Grace. I said Grace. Yeah. Okay, good. All right. Let's try this. Again, you're not gonna. Did we do this derivative actually? We did do it. Okay. Um, well, let's go on with just integrals. The integral of a function. A lot of you haven't got the integrals yet, but you will. I don't know. Do y'all get it in Calc 1 or just Calc 2? Oh, you do get the integrals in Calc 1. What's that? At the very end. Okay, and then Calculus 2, as I understand it, deals more so with it. But you biology majors won't go to Calc 2, as I understand. But you chem majors, pre-engineering majors, all you people, you'll go on and do Calc 2, 3, and even differential equations maybe. Um, but anyway, the definition, don't sweat this too much, but the definition is the limit as n approaches infinity of the sum of some function uh, Ci, I forget what Ci is. Oh, it's the value of a function at a particular point times delta x. So what you're doing here is you're multiplying two values and you're summing up those two values. You can think of these two values as being the area. In fact, you can think of these two values as being the height and the width, or the length and the width of a rectangle. Or you can think of it as a trapezoid too, but a rectangle is nice. And then all you're doing is you're taking the area of a rectangle. This is, say, let's see, this would be the height of the rectangle, and then this would be the width of the rectangle, the y value, the x value. And then you're adding all these things up. This is the Greek letter sigma. It's a summation. Right. And then you're taking the limit of that as you make n, which is the number of bins that you will put under this function, let that go to infinity. So you can look at this graphically, where this is my rectangle, this value is delta x, this value up here is f of ci, and then I'm just adding up all of those intervals as I go through a particular function. So whenever I think derivative, what are you thinking of a graph? If you take the derivative, you're finding the what of that graph? Slope, right? And if you take the integral of a function over a particular interval, what are you finding for that graph? The area under the curve. So we'll think about that. In fact, you'll have some problems where you have to manually find the slope or manually find the area under a curve. And then you'll also have some problems where you have to do it analytically. Actually, I'll give you the function, and you have to analytically find the slope. That is, take the derivative of the function, or find the integral of the function to find the area under that curve. We'll see that in the next chapter quite a bit when we get into kinematics. Uh, if some of you ever take numerical analysis, I know that some of you chem majors might go on and get a minor in math because you only have to take a couple more courses to get a minor. You should really take numerical analysis. When I was an undergrad, that was, especially if you're going to graduate school, when I was an undergrad, that was the most useful course that I ever had, was numerical analysis. It's where you're combining programming with algorithms, like for algorithms, say, to find an integral, and you calculate these integrals numerically. You do other things there too, like you solve differential equations numerically, you take derivatives numerically, all sorts of really cool stuff, but it's all where you're programming things, which if you go into grad school could be, especially if you chem majors, could be something that you do a lot. You engineering majors too. Um, so this is just an example of if I have a function, which is the black line, you can determine the area under the curve simply by dividing it into bins, like this. You determine the number of bins, that's that value n, and then you take the area of each bin and you add it up. You can do that in Excel if you want, but it's really easy to program it into C or whatever it is that y'all are programming in these days. What are y'all programming in these days? It's not C anymore, is it? Any programmers? Python or whatever it is that you use. No? Okay. Um, Mainly what we'll be doing in here are doing integrals of polynomials. And just like we had a formula, if you will, for finding the integral, for finding the derivative of a polynomial, we'll have a similar thing for finding the integral. It's 1 over n plus 1 times x to the n plus 1. So for example, here, I would have 3. My 3 would just come out of the integral. It doesn't change, so the integral of 3 is 3 times 1 over here, n is 2. So it's going to be 1 over 2 plus 1 times x to the 2 plus 1. And so that's going to be, these will cancel, 3 over 3, x cubed. All right? How about this function? This v equals 2t squared. What would be the derivative, or the integral of 2t squared? What would be the integral of 2t squared? I have b times x to the n in my formula. And so what is going to be the integral of 2t squared? What do I do to the exponent? I add 1 to the exponent. And then what do I do to the coefficient? I don't do anything to 2, but I have to add something else to the coefficient. I put it over n plus 1, right? So this would be 2 divided by what? 3 times t to the what? The third power. So this integral will be 2/3 t cubed. I would write that as the integral of v dt would equal to 2/3 t cubed. Right? So this is what this function looks like. It's a parabola 2t squared. I can estimate the area under this graph from t equals 0 to t equals 5. So I want to estimate the area from here all the way over to here. You'll need to do this on the exam, and you see some problems like this in the homework. Why I just have you estimate the area, and then you can go back and actually calculate what the area should be as well. So estimating the area, I look at each block. Each block here has a value in area equal to what? I go from 3 to 4 here. I go from 0 to 10 here. So this block has an area equal to what value? It has an area equal to 10, because on the x-axis, I go from 3 to 4 here, so that has a value of 1. I go from 0 to 10 on the y-axis, so on the y-axis, I have a value of 10. So each block here has a value equal to 10. Don't worry about the units just yet. It'll turn out that the units, though, are in distance units, meters. So I can have 10 there, I can have 10 here, 10 here. All of these whole blocks are 10. I'll call this 10. Let me get rid of that so it doesn't confuse us. What about this block right here? Roughly, what is it? It's about a half a block. We're just estimating, so we'll call that 5. And how about this block right here? We'll call it 5 too, right? We're just sort of estimating. This one might be a little more than 5 here. But look, I can combine both of these, and it looks like I get a full block. Right, so I'm just going to combine both of these and say that that's 10. And I'll take this little sliver and add it up to this little piece right here. And just as an estimate, I'll just call that 10. Okay? So you'll have some problems like that. You'll have some in the homework, but probably on the exam too, where I provide you a function, and you have to find either the slope or the area of the graph. Once we get into the next chapter, we'll begin to apply this. But then you just, in the case of finding the area, I just add these up. So I have 10, 20, 30, 40, 50, 60, 70, 80, 85. So my area under this graph from 0 to 5 is 85 units. Y'all clear on what I did there? Yeah. Sometimes your graphs will be more linear, in which case you'll just use a triangle. You'll create a triangle, and you'll need to know what the area of a triangle is. Of course, y'all know that. What is the area of a triangle? 1/2 base times height. Right? If you think about a square, its area is base times height. A triangle is 1/2 that value. Don't sweat it if you don't remember that right now. It'll come back in chapter 2, and we'll have to do it again. Okay, so the area under this graph from t equals 0 to 5 is 85 units. Turns out that those units are in meters. I can think about my dimensional analysis. I have meters per second here. I have seconds here. I can say meters per second times seconds, because that's what I'm doing, and it leaves me just with meters. So we'll see in chapter 2 that the area under a graph will give us distance traveled. Okay? And that comes out in the units, confirms that. Now I can also take this function, 2t squared, and integrate it. We've already said the integral of v dt, where v is equal to 2t squared. Gosh, what was this integral again? 2/3 t cubed. Remember, I add 1 to the exponent, and whatever that number is, divide that, the coefficient, by that number. So I have 2 over 2 plus 1, that's 2/3, and then I add 1 to the exponent to get me t cubed. Whenever you're doing integrals in this class, we'll never do indefinite intervals. We'll always evaluate them at particular intervals. And so here, I'm going to evaluate it beginning at my initial condition and going to my final condition. For the example we had on the previous graph, what are my initial and final conditions? What's my initial condition for time? Is 0. It's usually going to be 0 in this class, not always, but usually. And what's the final condition? 5, because I was integrating from 0 to 5. Let me go back to that graph and just show you, in case that's not clear. My initial condition, well, I'm starting here. That's my initial condition. And then my final condition, I'm ending here at 5 seconds, so that's my final point. So I start at my initial and final conditions and integrate over that. So that means I'll write it like this, t equals 0 to t equals 5. I'll write it as 2/3 t cubed. Or excuse me, I'm sorry, not 2/3 t cubed. 2/3 times 5 cubed minus my initial condition, which is 2/3 times 0 cubed. So what's 5? 5 times 5 is 25, 125, 150 over 3. So that's going to be, was it 83? 83. That's in meters. Gosh, what did we estimate the value to be? That's darn good, right? So we got a pretty good agreement on that. You should be able to know how to do both of those, but we'll work some examples in chapter 2 where we're dealing with position functions, taking the derivative of that, or taking the integral of a velocity or an acceleration function. So if you're not getting this, that's not a big deal, but you need to get it by chapter 2. Let's do this little quick test. What is the integral of this function? X is 3t to the minus 2. And there are your options. Right, doing pretty well. A few of you don't have the right, about 6 or 7 of you don't have the right answer, but feel free to ask your neighbor what they put. Remember, we're going to add 1 to the exponent and then divide the coefficient by that number that after we've added 1 to it. All right, I'll stop at 110, 110. Okay, awesome. A is right. Very good. Um, so I add 1 to the exponent. The exponent's here. -2 plus 1. That's equal to -1. And so I say 3 divided by -1 times t to the -1, which is the same as -3 divided by t. All right? Let's see. Do you know why gingerbread man never goes to the beach? He's got crummy legs. Not a very good one, is it? That's okay. Can't all be good, can they? All right. I don't remember if we finished all of these. I know we did a number of these. Did we do the dimensional analysis questions? Do you recall? In this one, the trig stuff? Yes. This too? Yes. Nearest y-axis? Sig figs? Okay, I guess we did it all. SI units, this one. Speed of y'all know what a knot is, by the way? Nautical mile per hour, right. This too. And sig figs, I think this is the last one. All right, awesome. I'll post those online. And I know some of you are starting to get your workbooks in. Those are also in your appendix, not with the answers, but without the answers. So next, in this chapter, when we start to do them, you can flip to the back and you can follow along in your workbook as you do. Okay? Chapter 1, that's the end of chapter 1. Hopefully you've at least begun on the homework, but you should certainly try to finish it up today or tomorrow. Because chapter 2, you don't want to get behind in chapter 2. Chapter 2 is not going to be really difficult, but it will be a little bit more of a step into where we're headed. And then chapter 3 will be even a little bit more of a step. And then chapter 4 even a little bit more so. So we're sort of ramping up to chapter 4. And then chapter 5 will sort of back up just a little bit. It gets a little bit easier in chapter 5 that we begin to see some new calculus things, the dot product, which you probably never heard of. And then in chapter 6 and 7, we'll begin to review some of the stuff that we do up to that point. Okay? I know some of you are feeling overwhelmed, like a good fraction of you are feeling overwhelmed. First week of class, you know, but um, come see me. That's my job. What's my job? What's my job? To teach, to help you do well in this class, okay? So that's my job. Let me do it. And they pay me what? Just a little bit of money or a lot of money to do that? Have I not had this discussion with you? Huh? Yeah, they pay me enough. I like their work, so they pay me enough. But that's what they pay me for, to help y'all do well in this class. Okay? All right. Let's move on to chapter 2. I don't usually do the homework in class. If y'all have questions about the homework, you can see me. But I think, you know, sig figs is stuff that you should all be fairly competent on by this point if you've been following along. Trig, estimates, dimensional analysis stuff. Some good extra practice there for you to have the exam. Some integrals and some derivatives. And don't forget, the solutions for the homework are online. And then also another good place for you to practice, if you're spending your 30 minutes a day or so on physics, another good place for you to practice is on the website. You can go to your course website, go to the old exams, Physics 201, and you can find every exam that I've ever given, and you can go through and practice some of these problems. Like, see, there's some dimensional analysis. Uh, that's all chapter 2 stuff. This is something like what we just did with a graph, finding the area under it and finding the slope of it. That's going to be chapter 2 as well. A lot of these free response are chapter 2 problems. Okay? So in the back of your workbook, there are exams from last semester. And as we get into more complicated material, we'll start doing some of those in class. But they're also good practice for you to do on your own. So if you're looking for stuff to practice, do the homework, do the old exams. All right? All right. People that do well in this class, they practice a lot. So keep that in mind. Okay, kinematics. We're just going to do one-dimensional kinematics. I wouldn't say this is easy, but it's a little more straightforward than when we get into two-dimensional kinematics, which will be in the next chapter. Kinematics describes motion. not motion, that's an N. Anytime we're dealing with systems and we're looking at the kinematics of a system, we'll need to describe a frame of reference. And all this does is it sets the coordinate system. We'll use our Cartesian system and the origin. So for example, if I have a car and it's traveling along with some velocity, all I'm saying is, look, I'm going to say that this is x equals 0, and any point that it goes from there, I'll measure from that point x equals 0. So a frame of reference is really just setting my origin and defining where the x and the y axes are. It's a really important step, and we'll see how that comes into play in this chapter and in the next two chapters. In kinematics, we're going to consider three things. We'll consider displacement, velocity, and acceleration. I'm going to define each of these here and how they're related to one another. If you've had physics, you've probably dealt with these some. Displacement, velocity, and acceleration. You can think of these as sort of progressing from one to the other. In fact, as we're talking about derivatives, the velocity is the derivative of the displacement. Derivatives describe how something changes, and so the velocity describes how the displacement changes. And then the acceleration, gosh, is the acceleration going to be the derivative or the integral of the velocity? It's the derivative, because the acceleration describes how the velocity changes. And so anytime I want to find the acceleration, if I know the velocity, that is a function describing the velocity, which is what we'll have, then I take the derivative of the velocity. It's a really nice application of Newton's invention of calculus in the motion. And that was his first application, actually, was looking at how things move and describing how things move. Okay, so displacement is just a change in position. So an x final minus x initial. So if I start at one point, let's say that my x final or my x initial, say I start at 0 meters, that will usually be the case. And then I travel to a certain place, say 5 meters from that point, plus 5 meters, then my displacement x will be equal to 5 minus 0, which is equal to 5. Let's watch a little clip here. This horse that's running around a track. What is his displacement? If I have a horse that's running around a track, this is my track. I think it's a mile or so on a horse track. If I have a horse, there's this tail, and he runs around the track, and he begins here, and he makes a loop around the track, then what is his displacement when he covers that mile distance? Oh, it's going to be 0, right. So we need to distinguish between displacement, which is a difference in initial and a final position, and distance that we travel. Because the horse clearly travels a distance of 1 mile, which is the length around the track, but his initial and final positions are both here. His x initial is equal to 0. That's where we set our frame of reference. And when he comes back here, our x final is also equal to 0. Right? So the displacement here then, delta x, is going to be 0 minus 0, which will be 0 meters. Even though the distance that he travels is going to equal to, 1 mile. So we need to draw that distinction in displacement that we can have positive displacement, or we can have negative displacement, or we can have no displacement at all, even when an object has moved around a certain path. Okay? I also like to show this because I feel like it's good to work with other people, especially if you're sort of coming into a subject that you're not real familiar with, because those other people, kind of like that second horse in front of Seabiscuit, the horse, Seabiscuit, he was sort of showing Seabiscuit that he could go faster. And I find that when you work with other people that they can show you that you can actually do more than you think that you can. Like we generally think kind of low of our ability when actually we can do things like physics and math with a little help. Okay? So if you feel that way, if you feel like you're just not capable, then I find that it's very helpful be with other people that know how to do it. All right. Let's um, let's consider this number line. We'll call it a graph of position. So uh, this is not a number line, but it just shows the position. So this is a position x equals 0. This is a position x equals -3. This is a position x equals 2. So let's say that I have different initial and final positions. Let's say that I have an initial position equal to 2 and a final position equal to 5. What is my displacement in this case? What is my delta x? It's going to be 5 minus 2, which is equal to 3. All right, I start here, I go here, my delta x equals 3 meters, going in this direction. All right, what if I have an x initial equal to 2 and an x final equal to -3? What then is my displacement? 5? It's actually -5, right. So here I can find this, I can just calculate it. I can say x final, which is -3, minus 2, which is equal to -5 meters. So if I go from 2 all the way over to -3, that's going to be -5 meters. I'll describe what that negative x is in just a moment. And then let's say that I go from x initial, x initial equals to -4 and x final equal to -1. What is my delta x in this case? It's going to be +3, right? So I'll do it in pink. So I'm going from here up to -1, up to here. So that's going to be +3. That's going to be -1 minus a -4. This becomes positive. 4 minus 1 is 3 meters. Okay? So we've introduced these signs. Here I had a positive, here I had a negative, and here I also have a positive. The reason we have these signs is because displacement is a vector quantity, and vectors have both a magnitude and direction. After this chapter, you'll get more vectors than you ever really wanted. But in this chapter, we're going to deal with vectors in one dimension, and the magnitude will just be the value of the number. Is it 5? Is it 3? Is it 2? The direction in this chapter, because we're just doing one dimension, will be the sign of the number. Is it positive or is it negative? Okay. So for example, if I have delta x equal to -2 meters, that means that the direction is negative, and the magnitude of this displacement is what? Is 2 meters, right? Negative is going to refer usually to left or down. So let's see, left is negative, right is positive, down is negative, up is positive, and there is a convention in the z-axis, but we're not going to deal with that now. All right, up is positive, down is negative, right is positive, left is right is positive, left is negative. Sometimes we'll give direction in other ways. You'll see this more so in chapter 3, but we can give north, south, east, west directions. So for example, if I have, say this is my compass, north, south, was it never eat, what is it? Y'all remember that from second grade? Never eat sour watermelon? Soggy waffles. Is that what y'all learned? Sour watermelon. Where are you from? Is that down the bayou? Where are you from, Mackenzie? Where are you from? Georgia. Oh, that's Georgia. Soggy waffles. No, my kids aren't in soggy waffles. BCA. All right. So anyway, um, in this case, we can define directions by angles. So for example, if I have a displacement that's in this direction, say 30 degrees, then I would say 30 degrees north of west. And we'll get into that next chapter. But you can use cardinal directions. You can also use, oops, never eat soggy waffles. Y'all know what I mean. This should be east. This should be west. So this would be north of east. All right? Okay. We can say up, down, left, right, or give it with an angle. We'll see that more later. Scalar quantities are some examples of vectors that we'll see in this class. Displacement, velocity, and acceleration. But also forces. What's another example? Oh, momentum, which we'll see in chapter 6, I think. Chapter 6. I think that's good. We usually show the variables for vectors with an arrow. So for example, if I want to show the velocity vector, I'll usually put an arrow over it. Sometimes people do different things. Sometimes they'll write vectors as bold print, like in a book or whatever, but usually you put an arrow over it. I get a little lazy about that as semester goes on. I won't write vectors with an arrow, but I will always give their direction. So you could have vectors with an arrow, your displacement like that, your acceleration, your force, or your momentum, which we're going to use a lowercase p for momentum. Scalar quantities only have a magnitude. So vectors have both magnitude and direction. Scalar quantities only have magnitude. What are some examples of scalar quantities? These are measurements that you make that have no direction attached to them. Mass is a scalar quantity. Temperature is a scalar quantity. Okay, speed is a scalar quantity. We'll talk about that. Speed is different from velocity. Speed is like what you read on your odometer, on your speedometer rather. It only measures the magnitude. The distance, right, that's different from displacement. Distance and displacement are different. So for example, Seabiscuit ran a total distance of 1 mile. He didn't run negative 1 mile. He didn't run 1 mile and 30 degrees from the x-axis. He just ran 1 mile, okay? So some scalar quantities include, as we said, mass, temperature, distance, speed. Also, time is a scalar quantity. On the test, you'll probably have a multiple choice question, and hopefully everybody get it right. But I'll give you some vector quantities, and I'll give you some scalar quantities, and ask you, what are these? Are these scalar or vector? It'll be a multiple choice question. Oh, like this one. Which of these is or are scalar quantities? I like questions like this where I give you multiple answers. It just makes you think a little bit more. So get used to them. I know y'all don't usually like them, but there are 4 things. Which of these are scalar quantities? I have mass, acceleration, speed, and velocity. One or more of those is a scalar quantity. Which is it? All right, I'll stop at 35. Okay, awesome. That's an easy one, right? So mass is a scalar quantity. Speed is a scalar quantity, so 1 and 3 is the right answer. Both of those are scalar quantities. These both, by the way, are both vector quantities. All right? Y'all okay with bar jokes? We're not like in a bar, but we'll just tell a bar joke. So a pony walks into a bar, and he says to the bartender, "Hey, give me a drink." And the bartender says, "What?" "Pony." Pony says, "Give me a drink." And the bartender what? And the pony says, oh, I'm sorry. I'm just a little horse. Yeah, I get it. Oh, you couldn't hear him. Yeah, okay. He's a little horse, pony. Okay, okay, let's look at velocity and speed. I'm going to go through and we'll define what each of these are. Um, so as we said, speed is a scalar quantity. It is the magnitude of the velocity. And we'll define speed in some other ways as well. We'll look at average speed, which is the speed over a particular interval as well. But if we're thinking about the velocity as having a magnitude and a direction, then you can think of the magnitude of that velocity as simply being the speed. We'll define the average speed as the total distance divided by the total time. And we can also write this as v equals d divided by t. When we're talking about speed, we won't write the little arrow on the top because it's a scalar quantity and not a vector quantity. You'll get used to that soon. So v is d over t. So if a runner runs a 400-meter track in 60 seconds, how would we find his average speed? I would do what? Just divide those two. So I would say distance over time. My distance is equal to 400 meters. Remember, no signs there. So I have 400 meters divided by 60 seconds. 0 cancels. What's that? 7 point something. We'll just call it 7 meters per second. All right. So that's our average speed. The average velocity in this case of a runner going around a 400-meter track, what would the average velocity be? Well, you might not know that right off, but what is the displacement of this runner? It's going to be 0, just like the horse on the track, because his initial and final positions are the same. So the displacement, delta x, will be equal to 0 minus 0, which is equal to 0 meters. Right? Our average velocity, that was average speed. Average velocity is going to be just a little bit different. It's going to be our displacement, delta x, divided by our delta t. So this is our displacement divided by time. It's going to be x final minus x initial divided by t final minus t initial. Almost always, practically always in this class, t initial will be 0. So I'll usually just not write t initial. I'll just say my t initial is 0. Average velocity is a vector with both magnitude and direction. So if I have the runner going around the track in 60 seconds, 400 meters, what is his average velocity? It's going to be 0, right? So because his final and initial positions are the same, and so that will be 0. The average velocity is going to be 0. It should be 0 meters divided by 60 seconds, which is 0 meters per second. All right, let's look at a plot. You're probably not going to have any problems like that where you're just calculating the average velocity of something, but you'll definitely have a graph that you'll need to analyze in a particular way. So this is a graph of position versus time, and I want to know what is the average velocity between the time of 0 to 30 seconds. Anytime I have a graph like this of position versus time, if I want to find the velocity, what do I want to find? slope or the area? If I want to find the velocity, what should I find? The slope or the area? The slope is right. And if you're ever uncertain about that, you want to look at the units. Because remember, slope is rise over run. Our rise is meter. Our run is seconds. So what are the units of the slope? Meters per second. However, the units of the, don't say this right away, but the units of the area under that graph, take just a second and think about it. What are the units of the area under that graph? All right. And what are the units of the area? Not meter squared. What is it? Oh, wanna. Meter seconds. Meters times seconds. Turns out that doesn't really mean anything. So we're not going to deal with the area of this graph, but we will see when we get to velocity versus time, as we've already done, that that does have a meaning. All right, so the slope of the line gives the average velocity from an interval of t equals 0 to 30 seconds. Right, so if I wanted to find that slope, I would do rise over run. My v would be delta x over delta t. I'm going to go back up to the graph. I'm going from 0 to 30. So that's going to be my delta t. And then my initial position here is minus 20. My final position is 40. So I'm going to have 40 minus negative 20. That's my initial and final position divided by 30. This is meters. This is seconds. So that's 60 over 30, or 2 meters per second. All right. That's easy peasy, right? Okay. You'll have some graphs. You'll have to find the area or the slope of them. And in this case, you have to find the slope. Because this particular line is straight, or is linear, it's a straight line. That means that the velocity doesn't change. The average velocity from, say, 10 to 30 seconds is going to be exactly the same. Because over the course of that line, as that object is moving, the slope doesn't change. If the slope doesn't change, that means the velocity doesn't change. And so the average velocity will also be the same. So I can look back at the graph. Now I'm looking, instead of 0 to 30, I'm looking from 10 to 30. So I'm going from this point to this point. My delta t now will not be 30 seconds, but it'll be 20 seconds. And then I'm going from 0 to 40. So when I put this in, it'll be 40 minus 20 meters. Or excuse me, not 20, it was, what was it? 0, wasn't it? Over 20 seconds. Write that out. That was from 30 minus 10. And so that's going to be 2 meters per second as well. Okay? Let me take a look at something. We might do some more problems right here. See where we are. We can do a few of these. So you and your dog go for a walk to the park. On the way, your dog takes many side trips to chase squirrels or examine fire hydrants or whatever. When you arrive at the park, do you and your dog have the same displacement? And again, if you're in your workbook, all these are in the back, so you can turn back to the last 30 or so pages, and all these questions are there. Do you and your dog have the same displacement? All right, I'll stop at 40 seconds. 40. Okay, awesome. A is right because you have the same initial and final positions. Excuse me. Even though your dog ran a much further distance as you went along, you have the same initial and final positions. Reminds me of my dog. I used to have a dog, Jolie. Y'all care? You care? Jolie, so I had her since she was just a little bitty puppy, and she died, I don't know, 10 or 15 years ago. But she was a great dog, and one time I took her out. We lived in Austin. We had like this trail that, is that your dog? Yeah. We had this trail where there was like next to a river, and she would like to swim because she was a golden lab mix. But she would jump into the river and swim, but I would just sort of walk along the trail, but she'd be going crazy, running all over the trail. And then I got home, and she had rubbed blisters on her paws because I was a bad owner. And then for like 2 weeks, or like a week maybe, I had to carry her outside to pee. I had to sort of carry her food over next to her, and she's just bedridden because she couldn't get up on her paws. Bad owner, right? Bad owner? Yes. Very bad. A good dog. Great dog. All right. Have you and your dog traveled the same distance? No, right? I mean, you're all fresh. Your dog has blisters all over her paws, for goodness sake. So, all right. If the position of a car is 0, does its speed have to be 0? Yes or no? Or does it depend on the position? Right, 35, I'll stop. 35. Feel free to ask your neighbor. Okay, B is right. The speed does not have to be 0, even though your position is 0. Here's a good example. Let's say I have this thing here. I call this position 0. I call any position I want 0, right? You too. It's not because I'm the professor who knows it. I can call whatever I want 0. And right now, the speed of this pen is 0, right? But I'm calling this point 0. Look, what if I do this? And then I let go of the pen. I'm still calling this 0. Is the pen going to have 0 speed at point 0? No, it's traveling at a significant speed at that point. So the position doesn't necessarily relate to the speed. Does the odometer in a car measure distance or displacement? All right, we'll stop at 25. 25. Okay, awesome. A is right. It measures distance because there's no direction in that. So if it measured direction, or in fact, not just direction, but it doesn't, when you come back to your original point, it doesn't take away miles like it should if it was measuring displacement. Very good. Let's see. Uh, Adam walks into a bar, says to the bartender, "Hey, I think I've lost an electron." And the bartender says, "Are you sure?" And the atom says what? I'm positive. Y'all have heard that one, right? Does the speedometer in a car measure velocity or speed? Velocity or speed? We'll do one more after this, okay? I know we're getting close to the end. But I'll stop at 23. 23. Okay, awesome. B is right. That measures speed because there's no direction. And then one more. Oh wait, no, we'll come back to this one actually. Uh, but I will see y'all on. I will not see you on Wednesday. I'll send an email out. I'll probably have some material for you to do outside of class, but I'll send that out this afternoon, okay? But no class on Wednesday, okay? I'll have some email, but otherwise I'll be mostly out of town.